Good morning, good afternoon, good evening, everyone. I'm Will Deacon. I'm going to be talking about virtualization for the masses, which is all about exposing KVM on Android. Super exciting. I've left this till the last minute, the recording, so we're going to do it in one take. So hopefully no deliveries halfway through. Let's see how we do. Introduction. So who am I and what am I hacking on? So I've been hacking on the Linux kernel for a while, but not so much with KVM. So this is kind of a lot of it's new for me. But yeah, active upstream kernel developer. I co-maintain, the big thing I co-maintain is the ARM64 architecture, along with Catalin Marinas from ARM. And as well as that, I'm also working on concurrency aspects, currency models, so locking, atomics, memory model tools, what else? TLB invalidation, good stuff there. And I also maintain the SIMMU drivers, which are ARM's IOMMU IP, essentially. So that's kind of the closest part I've got with KVM is the device pass-through and the FIO stuff. So last year I joined the Android systems team at Google. And I found myself leading the Protected KVM project there, which is a project to enable KVM on Android. It's a relatively new team, and lots of people on the team haven't even worked on Linux kernel before, so it's been quite exciting, ramping everybody up, especially remotely. Consequently, though, we've managed to come out as the top contributors to KVM for ARM64 for both 5.9 and I think for 5.10 as well, looking at what's queued for the current merge window. And there's tons more to come, because what we're working on seems to be a hot topic, not just on ARM64, but for other architectures as well. So I'm very keen to hear from other people, whether it's in the questions or in emails about other efforts to do similar stuff to what we're doing. And a disclaimer before we jump in, this is all very much a work in progress. We are upstreaming as we go. We don't want to fall into the old trap of doing a whole load of stuff out of the tree, particularly for Android, and then throwing it over the wall at the community and say, there you go, have at it. Because often that doesn't get anywhere upstream, and it's not a very good way of building up a decent solution involving the community. So we're upstreaming as we go. Some parts of the code we're pretty confident with. Some parts we don't really have much of a good idea on yet. We're open to change. So please get in touch if you've got ideas. Mostly it works all right. For things like user ABI, obviously we're not upstreaming that as we go, because you kind of need to get that right. But for implementation stuff, it's a good approach. So before I talk really about the KVM side of things and the virtualization side of things, I need to talk a bit about the state of modern Android to motivate why we're doing what we're doing, and to give you an idea of some of the problems we're facing. So the sort of latest thing in the Android system space for modern Android is this thing called the generic kernel image, or GKI. And you might have heard of it. There's a link here at the bottom where you can read loads of stuff about it on the source at android.com. There's also some LWN articles. It's been mentioned at Linux Plunders, I think, at least once. And what this generic kernel image is about, it's about attacking this problem that we have traditionally, there's a separate kernel for each Android device. So you have different Android handsets, they're all running their own kernel. Clearly this doesn't scale. It leads to horrible fragmentation, and the problems associated with that fragmentation include the inability to update those systems, because it's difficult and expensive if you have to deploy a separate kernel update for every single device, because they're all running different kernels. It just doesn't scale at all. This also can make it impossible to upgrade from one Android release to another for a given device, because that new Android release might require a kernel feature that's not present on that device, and there's no way of doing a upgrade to that kernel which introduces the feature. And I think also, and there's a point that doesn't get made quite enough, it is bad for upstream, because the upstream kernel, the job of the upstream kernel is to have the right subsystems and the right abstractions in place that we can support all these different devices to get the generality right. And you can't do that unless you have visibility into all of the different problems out there, and the different devices and different pieces of hardware and different solutions even. And because it's all squirreled away in these different kernels, it's very hard to see the wood for the trees. You can't quite come up with an abstraction that will work for everybody. It's difficult. So GKI aims to solve basically this fragmentation problem. And the way it does that is by sort of rallying around a single kernel image for a given Android release and kernel version. So here I've said, Android 11.5.4, this would be a given GKI kernel. And for that kernel, which is only ever the 5.4 kernel for Android 11, a subset of the module ABI remains stable. What this means is you can build a binary module as a vendor. You can have a driver, which is a binary module, against this branch, and as the branch is updated with sort of LTS and security updates, we will guarantee, as the Android systems team, we will guarantee that your modules will continue to load into that kernel. So this means that the vendor portion, i.e. device drivers, can be deployed independently of the core kernel image. And it also means that you can have a core kernel image that's shared across multiple devices, and then we can have LTS updates, as long as we don't break the ABI. Now the ABI, I mean, I can probably hear you screaming, kernel ABI, oh, it's the worst thing, you don't want to do it, don't do it. Well, like I say, it's only for a given Android release and kernel version, so it's kind of over LTS merges, but also it's not for the whole of the kernel, it's for an allow list of symbols, which we explicitly say we will maintain these. So that's the idea of GKI, solving the fragmentation problem for the kernel. So what about the hypervisor? Well, let's look at virtualization on Android today. And if you think fragmentation for the kernel side is bad, I mean, this is much, much worse. At least with the kernel side, everyone's using a different version of Linux. Well, with hypervisor, it's totally crazy. I said it's the Wild West of fragmentation. Some devices don't even have a hypervisor. So, that's one possible configuration. You don't have to have one. You just kind of ignore that exception level. Many devices do, but it's a hypervisor gym, but not as we know it. If you look at some sort of three things that people do with the hypervisor here, I've listed them, just these bullet points. So the first one here is security enhancements protecting the kernel. So some people put code in the hypervisor which allows the kernel to make hypercalls to change permissions on pages and things like that. That's all well and good, but the thing to remember here, obviously, is that the hypervisor itself is running with elevated privileges. And mitigations are attack surface too. If you stick that string into your favorite search engine, there's an great article from Jan Horn at Project Zero showing actually how you can attack and exploit vulnerabilities in some of these security enhancements. The code that's protecting you is actually itself it's vulnerable, so it's not protecting you at all. It's introducing more issues than it solves. Two other things here: coarse-grained memory partitioning. So many of these devices feature something that looks a little bit like an IMMU, but if you look closely, it's not. Often you don't have translation, or you might not have page granular mappings. But what you can do with this hardware is sort of carve up the physical address space. So early during boot, you just do this thing once. You say, well, this piece of memory, this guy can DMA to it. This piece of memory, the CPU can have. This piece of memory goes to the radio. And that's okay, fine. I get why that needs to be done by the hypervisor at boot, but then that kind of code doesn't really do much after that, and it just feels like a big waste of the exception level. There's a lot more you can do than just carve up your physical memory once. And this third point is my least favorite: running code outside of Android. I mean, put simply, the hypervisor exception layer is a place where you can put code, and it's not firmware, so you don't have to worry about bricking the device, updating it. And it's not the Android side of things, so you don't have to worry about having to integrate with anybody else. So it's like a little bit of a playground where if you've got some code you don't know where to put it, well, I'll just stick it in the hypervisor layer. And that's really bad because it's then running with privileges that it really does not need. I think the takeaway as well here is most of the time, down here, there aren't even any virtual machines. What kind of hypervisor is this? It doesn't really offer much in the way of hypervisor-like services that you might hope for. And my conclusion on all of this is I think both security and functionality lose out. Security loses out because you've got an increased TCB. And updating this thing is difficult because of the fragmentation. And similarly, functionality loses out, again, because of the fragmentation. It's not possible to expose a portable sort of hypervisor or virtualization API to Android applications or even the Android host kernel, because it's all so different. You can't leverage any of this stuff, and often it's just locked down anyway. So to give you probably a more concrete flavor of exactly how this stuff fits together, we need to go through the ARM v8 exception model here. This is the sort of traditional view that you would get if you ask somebody familiar with the ARM system architecture, tell me about the ARM exception model. They would give you this picture, and there's lots of versions of this picture on the internet. So down the left-hand side, we've got EL0 to EL3. So EL3 is more privileged than EL0. EL0 is user space, apps. EL1 is kernel, as you can see, there's a couple of kernels there. EL2, hypervisor, EL3, firmware. And I think the interesting thing probably here is this dividing line down the middle which partitions EL012. It kind of mirrors it. And on the left side, we've got this non-secure, sometimes known as the normal world. And on the right-hand side, we have the secure world. And the difference between these two is a bit on the bus, which tells you whether you're non-secure or not. But this is a way of running these so-called trusted operating systems or trusted applications in some memory, some physical memory, which is otherwise inaccessible to the normal world. So you've got some sort of isolation. This has been in the ARM architecture for a long time before we had any support for virtualization. And I'm going to talk a bit more about this because this is important as a motivator for why we're doing what we're doing. Because if you take this diagram and you reorganize it in terms of what I'm going to call privilege, which is your ability to access physical memory or map physical memory, it looks a bit like this. And you'll see that I've put the secure world basically underneath the non-secure world, where the lower down in this stack you are, the more privileged you have. And the reason I've done that is because the way the architecture works is that secure world can access all of non-secure memory. You just have to set a bit in the page tables to say, hey, I want to map this non-secure. But you can't do it the other way around. So non-secure world cannot map secure memory. If it tries to set the bit to say secure, it's ignored by the MMU. So this means, if this trusted OS wants to, it can map all of hypervisor memory. And worse, if it offered some sort of wacky mmap call down to this trusted app, maybe the trusted app can also map all of hypervisor memory. And I mean, this is bad for a few reasons. But if you map it to how it looks on an Android system, so we can first of all get rid of a few of these boxes. We don't have any virtual machines, as I said. We don't have this because the hardware doesn't yet exist for any of these bits. When you look at these boxes that are left, it's bad because Android is running up here. So Android is now sort of the least privileged part of the system. And so this includes the GKI we talked about, and the modules, all of the system libraries, the apps, and this is what people kind of call Android. Hey, I'm running Android, even though you've got all this other software. This is what people would normally think of as Android. So Android, which is the part that we're trying to update. You get apps being updated over the Play Store because they've got a security problem. Well, okay, that's fine. But what about all this stuff running on top? And what kind of stuff does run on top? Well, over in the secure world, you might have DRM in there. You might have crypto in there. Now, why DRM would need this sort of elevated privilege to have access to all of hypervisor memory, I don't know. But it's an unfortunate side effect of the way this is architected. Third-party OSs, opaque blobs, and it's integrated per device, which means you've got the fragmentation problem I've been talking about for most of this talk so far. You'll notice that all of the software that runs in that secure blob is typically prefixed with trusted. If I go back one slide, you can see there's a trusted OS, trusted app, trusted partition manager. Right. And I think the reason is here just marketing. This is a technology that ARM calls trust zone. And it's to give you to feel that something is safe and reliable. But another definition is to expect, hope, or suppose, definition of trust. And the unfortunate reality is that Android hopes that this software isn't malicious or compromised, because if it is, there's nothing we can do about it. We're running right down in that tiny little corner, deprivileged. So what we want is a way to actually deprivilege this third-party code. We don't want it running up in secure world. And we want to provide a portal environment so that those trusted software can be isolated from each other, but also from the rest of Android. So put a red arrow on that diagram. Put simply, why don't we move all of this into a virtual machine? Because we haven't got any, right? There's a nice space here, a nice gap. It fits right in there. And now it can't, arbitrarily access the normal memory because it's going to be managed by this hypervisor. But what about that hypervisor? What's going to live here? Well, the idea is that we can leverage the GKI effort, right? GKI is about shipping this single kernel binary, which should work everywhere. Well, that's based on Linux. Linux has KVM. That's a well-supported hypervisor. So maybe we can leverage the GKI effort, and as well as putting GKI kernel here, we can also put KVM at this hypervisor. That's the idea. So now let's move on and talk a bit about what virtualization looks like on ARM64, and in particular how it's used by KVM, because there's a couple of modes, and it's important to see why they don't both work for us, what we're trying to do. So let's just quickly run through the checklist to make sure this is even remotely feasible. Well, the good news is that all ARM64 Android devices have support for hypervirtualization. It's hugely underused technology because of the fragmentation, but the CPUs support it. They have a two-stage MMU. It's nothing particularly bizarre here. You've got a stage 1 translation, which is a set of page tables that are owned by the guest, and the output of that, the guest reckons it's a physical address, but it's not. It's an intermediate physical address, and that goes as input to a second stage page table that's owned by the hypervisor to actually do that translation. And so these stage 2 page tables allow you to provide memory isolation because you can carve up your physical memory and donate different bits to different guests. So yeah, our idea is to move out this third-party code to improve security. And in the end, we want a common hypervisor in Android so that we can have competency of data and integrity of computation for applications for new use cases as well. So how does KVM fit in? KVM has been supported for a while on ARM64 since 3.11. I mean, ARM64 itself was only supported, I think, in 3.7. So it's been there almost since the beginning for us. And it's curious because it can run in one of two modes, broadly speaking. So back to these sort of exception level diagrams. On the left here, we've got the sort of traditional one that I showed earlier on. So EL2 is our hypervisor. So this is what's known as nVHE. I'll come on to what that means in a minute. This is in 8.0. So all ARM64 CPUs can run in this mode if they want to. The hardware supports it. So you have your VMM down in host user space. Could be QEMU. And then you have your host kernel, which is so far so good. Flipping over here, you've got a guest kernel also running EL1 with its applications. Okay, great. But because of this hypervisor layer, you can't actually jump directly from the, you can't set up an exception, as it were, exception return directly from this host kernel to this guest, because you don't have the privileges to access the system registers and things like TLB and validation instructions, all that kind of stuff that you need to be able to do the context switch. So what happens is you have to hypercall up to EL2. So if the VMM does vCPU run, that's going to be an ioctl to host kernel. That will do some mucking about, and then it will do a hypercall up to say, right, I want to run this vCPU. We then have what we call the world switch, which just switches all of the register state and then exception returns back to the guest kernel. So that's how it works on a V8.0 system. And obviously the problem here is that you end up jumping around quite a lot. You have to keep going up and down from this world switch code, which can add latency to things like an MMIO exit, where you've got to go up from the guest, back down to the host, back down to the VMM, if it's handled in user space, then back up, and then down again. So for 8.1, which is kind of the iterative release of the architecture, these things called the virtualization host extensions, which is VHE, so this is non-VHE. They added some tweaks which actually mean that you can run the host kernel directly at EL2. The reason we can't do that over here is that this EL2 environment is quite constrained. I'll talk more about that later, but you can't run a Linux kernel here without VHE. But with VHE, you can do that, and you don't have anything here. You can just exception return straight back down. So this is blazingly fast, 111. But the problem with this is that although this is fine for KVM, it really shows an issue with the threat model of KVM when compared to the threat model for Android. The threat model of KVM, it places the entire host kernel and the VMM via these ioctls into the TCB. Because the host has full access to guest memory, the VMM has full access to guest memory. All of the memory over here is accessible to over here. And I said it's a bit like an inverse trust zone, because before, if this thing here, if this guest kernel used to run in secure, it was the one with access to everything, and now it's not. But the host kernel has access to everything. So I think we've just inverted the problem. So here's the big problem, which I accidentally switched to earlier on. But the big problem is the security model of Android is not aligned with this. The current design of KVM, which says that the host and the VMM have access to all of guest memory, is a big no-no for Android. The Android security model requires that guest data remains private, even if the host kernel has been compromised, which is practically impossible, I think, to achieve with the VHE case, because your host kernel is running at the hypervisor level, but you've given it that privilege. But with nVHE, maybe it's not so bad, because we've got that piece of world switch code. So what if we extend that world switch code? So we trust that, but we don't have to trust the whole Linux kernel that's running in the host. So we basically improve this world switch code so it can manage all of the guest memory and doesn't let the host kernel have access to it anymore. So we can install a stage 2 translation now, even for the host kernel during boot, before we load any of these third-party vendor modules. And we can use message passing for the host and the VM to communicate. And we need to make sure that the host doesn't tamper with the VM images. So we'll have to have a special bootloader that does some signature checking. And while we're at it, we'll try and apply formal verification techniques, because the EL2 code is drastically simpler than Linux. It's much smaller and cut down. It's not doing an awful lot of stuff. Even after we start extending it like this, it can't schedule, for example. It doesn't have preemption. So we can try and reason about its correctness and perhaps even prove some isolation properties. Open question here. Another alternative would be to run Android in a VM. I think that's plausible. It has a different set of challenges. I don't think it's obviously better. Either way is obviously better. I mean, running in a VM, there's a latency overhead with things like interrupt delivery. And there are also additional hardware requirements. Like now you really need to be able to pass through devices. And the iMenus that we're seeing aren't quite up to that sort of job to do it more generally. So roughly here's what the flow might look like. So you've got the GKI kernel, but now it's shipped with a hypervisor. Hooray. During boot, it deprivileges, which leaves this protected KVM, we're calling it. So that's your EL2, was just the world switch code. It's doing a bit more. And then we can start loading modules, and this KVM here is going to be setting up stage 2 and things like that. So what do we need at EL2? Because this world switch code doesn't do very much at the moment, we need to tame it. It's a pretty horrible place. It has its own limited virtual address space. So it doesn't have quite the addressing capability as EL1 does. It only has one page table base, for example, which makes some things challenging. You cannot run general code there, not least because it's not preemptible or interruptible, so you can't block or schedule. But also, some of the registers haven't quite got the same names and stuff like that. EL2 can access all of normal memory if mapped. So again, we don't want to run lots and lots of code over there, because if we end up running lots of complicated code over there, we kind of have, defeated ourselves in the sense that we're trying to reduce the amount of code that has access to guest memory, whereas EL2 does have access to that if it decides to map it. There's very limited device access at EL2. Again, the host kernel normally deals with devices. So typically you don't have a console at EL2. We've got some hacks for the debug console, but typically you don't even have that. It's just kind of the level of device access you have. It's normally none. And it's just doing this context switching that I was talking about earlier on. It's quite interesting. Prior to 5.9, there was this macro in Linux called KVM call hype, where you pass a function pointer in here from your host kernel. And basically, if that function is in the hypertext section of the kernel image, then it will just run at EL2. So this allows, whilst this allows the host kernel, just to run code at EL2, it's obviously a big security problem. I'll show you a bit about how that was implemented. So here's a call site here, KVM call hype, and in this case, we're trying to flush the TLB. So then that calls this macro, which this KVM ksim-ref basically converts this function pointer into a linear map address because we have an alias of the linear map to EL2. Then it makes a hypercall. So everything above this dotted line is hypervisor. Everything below this dotted line is the host kernel. So then we come into the entry dispatcher. This converts that linear map address into a hypervisor address. It's just an offset. And then this is the crazy part. This do EL2 call is literally an indirect call. It's an indirect branch. So it just branches to whatever address came back out of here, which hopefully, if the host was being nice, we get here. And if we went off into the weeds, who knows what will happen, right? So you can see all that code here. We need the EL2 code to be self-contained and safe against a compromised kernel. And very clearly it's not. You saw on a previous slide, you can just essentially pass function pointers up and have them run. So we've been trying to improve bits of this. So I'll show you some of the changes we've been making. So one of the changes we've made is actually, instead of having a run arbitrary function, we're changing to a fixed set of hypercalls for each individual service we need to offer. We've also worked at embedding the EL2 payload into its own partially linked object so that we can reason about the symbol references that we have. So we're trying to reduce the number of symbol references we have to the kernel text and to the kernel image. We want to have this whole thing self-contained. So an example here. It's a good quote I saw the other day. I don't know where it's from, but who needs namespaces when you have underscores? So we've used that similar to the way we do with the FI stub. So every symbol inside this KVM nVHE object, which is our partially linked EL2 code, gets prefixed with this KVM nVHE, and that's what stops us accidentally referring to other symbols. So you can see that the thing that we ran earlier on, the KVM flush VM context, has now got that there. And then we can have an allow list, because in some cases we do have to access kernel symbols. We can't dereference them unless they're mapped, but we sometimes need to perform some arithmetic based off them. But at least now that's an opt-in rather than just an implicit. You can refer to stuff and can't really reason about what's going to work and what's not. So anyway, with this object embedded in the kernel, during boot, we install it, then we deprivilege. Before we deprivilege, we flip all the static keys, do the runtime patching. It doesn't mean once we've deprivileged, you can't flip any static keys in the EL2 code, because if we allow the host to modify hypervisor text, we've lost. And then after deprivilege, the EL2 object is actually just completely unmapped. Well, it's not at the moment, but it will be unmapped from EL1, so you won't even be able to read it anymore. So in 5.9, 5.10, this is stuff that's gone in or going in. That call now looks like this. So the KVM flush VM context actually gets converted by this macro here into a constant 2. So instead of passing a function pointer, we pass a number 2, and the EL2 entry dispatcher, so above the line, we're in the hypervisor. Well, it's now written in C, which is a bit easier to read, and we can just switch on the function ID. So it's much more sort of fixed function for operations rather than arbitrary function pointers. And this code is all moved into an nVHE directory. So it's a bit easier to reason about. That's partly because we're building that partially linked object in there. So that's all good, but there's still some major problems. And some of these problems, well, yeah, pretty much all of these problems fall down to the way the virtual memory is managed. So the host kernel is in complete control of the hypervisor virtual memory. So your hypervisor stage 1 mappings here are created by the host. So that's obviously bad, because it means that, okay, you can make sure that it's all self-contained and doesn't have arbitrary function pointers, but the host has the page tables for the hypervisor code and hypervisor mapping, so it can just mess around with the page tables and have it do whatever it wants. What's worse is the hypervisor pages are also mapped by the host linear mapping, so you can even just directly write to parts of it if you wanted to. There's also some funny behavior. I find this quite odd, but with the current KVM approach, the KVM data structure, things like struct KVM, they get mapped to EL2, which you need it for the world switch. But as there's no unmap, so as time goes on, EL2 gradually just gets mappings for more and more of kernel memory. If you spawn a VM, EL2 will map the VM data structures. The VM exits, that memory will be freed and used for something else, but EL2 still just has this kind of dangling mapping to it, which isn't great for a security point of view. There's a homebrew per CPU implementation that just directly reuses the host region, so we need to separate that out. And it's not just the hypervisor stage 1 mappings, it's the guest stage 2 page tables as well, are also managed by the host kernel. And so EL2 just blindly installs them. So the host kernel sets up the stage 2 page table, and during the world switch, we just plumb up the root pointer and hope that the host has set them up correctly. And as a side effect of the host managing the page tables, they just happen to be constrained by the host page table configuration. So the page table construction all uses, the usual Linux abstractions of PGD, PUD, PMD, but it means that things like the stage 2 of a guest is sort of artificially constrained by what the host can address, or the way that it's been configured, which is just undesirable. It's not a security problem, it's just undesirable. For the rest of this stuff, I said here, it makes it trivial for the host kernel to bypass any hypervisor restrictions. Hopefully you can see that. I mean, yeah, there's basically no separation between the two. And this is without pKVM. So work that's ongoing. Some of this has landed in 5.10 or will land in 5.10. The pull request is out to Paolo at the moment. Other bits we're targeting 5.11, but basically it's preventing the host kernel from accessing these page tables directly. So for 5.10, we've got a complete rewrite standalone page table walker. So this is good for a few reasons. One, because it means that the host configuration is independent of the stage 2 configuration now. And also, it's actually more efficient and less code, so it's generally a good cleanup. But the main thing is it allows us to instantiate a page table allocator at EL2 directly and stop the host having access to those page tables. Problem with that, of course, is that in order to allocate page tables, we need a memory allocator, and we don't have a memory allocator at EL2. So that's work that's ongoing for 5.11. The idea is that there's a hypervisor carve-out that's donated during boot, but we still need an actual, a proper allocator on top of that. And the way it works with the bootstrap is that the host, before the host deprivileges, it allocates some temporary page tables, calls up to EL2 to get it going, and then EL2 bootstraps itself, and then the host can free the old page tables after deprivilege. I'll show you some code for that in a second. We've got a new complete standalone per CPU implementation. So it's the kernel per CPU implementation, but instantiated again with a separate region. So we don't have to borrow any of the host per CPU region. And eventually we'll need to keep the IMMUs in sync as well to make sure you can't do DMA attacks to access guest memory. So here's some more code. If we look down at the bottom, so again, below the line is the host. In the CPU init height mode, so this is the very first thing we're going to do, is we want to install some vectors into the EL2 so that we can do the bootstrap. Because initially there's just some stubs in there, which were installed when we were still booting, but for the first time from the bootloader. So we get this vector, we pass that up, and we also pass a temporary page table, which is this PGD pointer, and some temporary stack and things like that. Then what we do is we instruct the hypervisor with this KVM hype setup call to actually bootstrap itself. So, okay, you're running on my temporary page table that I've given you. Please go and create your own, set up your allocator, and deprivilege me. So here we pass in a whole bunch of other things. But the main idea here is that after this is returned, we can free, this is actually this PGD here, we can free the old page table because now EL2 is completely running self-contained. So over at EL2, this leaves us in a state where we have an allocator. So this is a basic buddy allocator we have for page allocation. We're trying to follow as close as we can the MM design for the host kernel, just massively simplified because we don't need a lot of the complexity. So we have a buddy allocator. We can allocate pages, only pages. We don't have slub or anything like that. There's a height pool and an order, and the pool is just protected with a lock. We're just using very coarse locking. It works fine for what we need. And we have a struct height page, which basically contains the pointers into this free list, or this set of free lists. And that's in the hyperVM map, so we can track each page, each physical page that is owned by the hypervisor in there. Now, the interesting thing is with all this page table code now running at EL2, it means when you spawn a guest, the guest memory is unmapped from the host. And Linux can't really deal with that, right? Because it's not like memory hot plug where you lose a whole bank. It's just you lose whatever pages were assigned to that guest. So memory will disappear from the host as it's assigned to a guest. And there's this patch series that isn't merged, but it's been on the list for a while. From Kirill Shutamov, he's one of the main MM maintainers. So if it's from him, it's probably not a bad idea. It's got some chance of going in if we show that it's useful to us. So we will definitely need this on the host, so that pages can disappear as they go to the guest and then reappear as the guest is torn down. And there's some questions here about what we do if the host accidentally accesses that. IMMU support, again, I mentioned that earlier, we need it to prevent DMA attacks. It's an unfortunate reliance on SOC design. The SOCs out there aren't quite ready for this kind of stuff, but we'll see what we can do. Ideally, we would have, an IMMU which could just simply reuse the page table that was installed in the CPU. So very little in the way of device management at EL2, because what we don't want is to have lots and lots of IMMU drivers at EL2 and then have this big pile of code that both duplicates logic that's in the host kernel, but also makes things like the formal verification efforts or just even the compliance for security requirements make that very difficult to verify. What else? So yeah, I mentioned earlier on about, right at the beginning, about hypervisors being used to provide security enhancements for the host kernel. We could, in theory, do something like that. Right? If the host has a read-write entry at stage 2, it could ask the hypervisor to change it, maybe to make it read-only. And it appears to the host like the permissions have changed for the physical memory. So it's quite an interesting defense mechanism there. And another thing is that the VMM will now not be able to access any of the guest state. So that's clearly going to cause problems. The main problem it causes is Virtio, which I'll talk about a bit in a minute. And there's interesting questions about how do we initialize the guest to begin with. So initializing the guest to begin with, we're going to be using this template bootloader. So it's very, very small bootloader, planning to try and write this in bare metal Rust. And the idea is that actually when you tell KVM, hey, I've got a protected VM, the hypervisor will, instead of entering the VM directly, instead of the VMM setting the PC and saying, please enter it here for the vCPU, the hypervisor will actually run this template bootloader first, which will be specified in a carve-out and provided by the host prior to deprivilege. And this template bootloader basically has 2 jobs. One is to signature check the payload that's coming up, just some sort of hash or public key or something like that. And then if it passes, to jump to it. That's roughly how that's going to work. So we've got some ideas for exactly what we might do here. So the template bootloader probably run in a restricted environment where you can't have things like MMIO exits and stuff like that. We really wanted to run a very small piece of code. The payload itself will have a proper second stage bootloader that we chain loaded. None of this really needs to be ARM64 specific. So if anyone else thinks this would be useful for them, or they'd like to talk about it, or they've got ideas, or they see problems with it, please let us know. Because we're just about to start, really implementing this in anger, and I'd like to hear thoughts before we have, if we've got something that then works and someone says, oh, by the way, can you make it work in the architecture? It would be nice to know earlier. So just to finish off, the last section of the talk is about the virtual platform that we offer. So we're adapting crosvm as the VMM. So crosvm, there's loads of talks about this at KVM forum. You can seek them out. It's part of the Chrome OS distribution. It's now included in Android. We've got a copy of it in there. It's a modern code base written in Rust. And the reason we're using this, well, there's many reasons, but one big reason is that there's a focus on security and sandboxing, which really fits our need. And also because we're lazy, and crosvm has a decent selection of Virtio devices implemented. Like, I think it can run Android now, so that's a big deal for us. One thing that is surprisingly important here is that we need this whole solution to be cross-architecture. You might think, especially as a talk from me, the ARM64 co-maintainer, you might think that this is all a big ARM64 play. It's not. It really needs to be cross-architecture. You can learn about this virtual platform we have called Cuttlefish, which is used actually for lots of our Android pre-submit testing. That's an x86 platform. So we need this to work on x86 and ARM64. So cross-architecture is very important to us. CrossVM is cross-architecture. But on the ARM64 side, the virtual platform we provide looks very, very straightforward. It's a fixed memory map. We're using the standard PSCI firmware calls to bring CPUs online. We've got the architected timer. We need to offer entropy service. There are patches, I think, from ARD on the list to do that, to make sure that we can get crypto working early. One thing we're doing differently from the architecture, so normally you'd have the GIC, which is the generic interrupt controller. It's the ARM architected interrupt controller. The GIC is a huge, huge beast. It's very, very complicated, and it requires lots of complicated code at EL2, which is exactly what we don't want. So we're investigating a para-virtualized interrupt controller known as the RVIC, and you can see Mark Zangier's talk. I think it's at some time, it's early in the morning tomorrow, I think, or maybe Wednesday, I can't remember. Have a look on the schedule and see what that's all about. So what about I/O? Well, we should just use VirtIO, stupid. It's the best thing since sliced bread. Use it for everything. VirtIO is great. I love it. So is the job done? Well, not quite, because VirtIO assumes that you have access to all of guest memory from the host. So down here, it assumes that guest memory is shared with the host. It also, VirtIO then means that even if you get it working, the host can intercept data. So you have to use crypto, and you have to use quite clever crypto. For example, things like FS-Verity, which you can read out here in the file system. And we'll need some modifications there because I think it's currently just done at open time. We need it probably done at read. So we do need to make changes, but we really don't want to have to change the spec. We might need to add things to the spec, like maybe new devices, but we don't want to make radical changes. And the big problem we've got with Virtio is there is no shared memory device, which forces us to use bounce buffering. So we have this working via these shared windows. So in Virtio 1.1, you can set this flag in your device called faccess platform, which indicates that the device access to memory is limited, which maps what we're doing, right? It does have limited access to memory. You can't access any of it. And when Linux sees this is set, it uses the DMA API for all Virtio allocations. So for the rings and also for mapping and unmapping. So what we can do is we can set that flag in the devices in crosvm. We can tell the guest kernel, if it's Linux, please use bounce buffering for everything. And then we can hook the set memory decrypted encrypted API in Linux. And as a hack at the moment, you basically need to make some hypercalls to share and unshare the pages back with the host. So it's a bit weird because it's not really encryption, but it does map quite nicely. So if you decrypt a page, you share it with the host, and if you encrypt a page, you don't give the host access anymore. And that works. I mean, we have this working. It's just, it means that you bounce buffer everything. And if you want zero copy for better performance, then that doesn't work at all with this approach. And so some cases, for example, buying a shared memory requires zero copy. And zero copy is really quite difficult because you have to have a handshake from the host and the guest. It's like a three-way handshake involving the hypervisor to make sure that the guest can't just decide to access host memory, but also so the host can't just randomly screw with the stage 2 for the guest. So you kind of have to have the host say to the hypervisor, hey, I'd like to do a zero copy for this page. And then the guest also say to the hypervisor, yes, I agree to set this page up for zero copy. And then they have to talk to each other to work out exactly what they mean, and then it gets set up. So it's a bit fiddly. There's a specification from ARM called FFA. It's changed name at least 3 times, but at the time of writing, it was called FFA. So they put a lot of thought into that memory handshake, and it's worth having a look at the spec. The problem is the spec itself is fairly heavyweight. It covers a lot of other things like scheduling, and it covers things like message passing, and it's not cross-architecture. So we really need cross-architecture, and we don't need any of the scheduling here. So an open question here really is what should we be using? I'd really like to know how other people managed to set up this zero copy shared memory between host and guest with a limited addressing environment. I've looked at things like IVSH mem, and it doesn't, I mean, that's not even supported in mainline, I don't think. But we do need a solution here. So what's next? Loads of other stuff to do. Complete the bootstrap, stabilize the user ABIs, figure out what we're doing for zero copy. We need to move more of the guest state up to EL2, and things like the vCPU state and stuff like that. Memory poisoning on reclaim, proxying firmware calls. Attestation is really important because the guest needs to be able to figure out that it really is running under the protected KVM hypervisor. Ballooning for reclaiming guest memory. Integration with the rest of Android is quite interesting because this whole talk is a kernel hypervisor talk, and I'm a sort of kernel-y hypervisory kind of person. I kind of underestimated how much effort this is, but getting all of this to work nicely with the rest of Android user space is a big task. And we'll just keep upstreaming. Any questions? We've got a list which you can CC on patches if you like. It's not archived, but you can get in touch with the whole team here, or just the KVM ARM list. We're on there. So thank you very much.